Hello and welcome to the last tutorial for Math 115. My name is Matthew Harris and I'll be the instructor going through the tutorial this week. So for the first question, we're asked to find the eigenvalues for this matrix A given by this thing here, and for each one of these eigenvalues we want to find one corresponding eigenvector. So without further ado, let's get into it. So the first thing we want to do is find the characteristic polynomial for this matrix A. How do we do that? Well, by definition, the characteristic polynomial is simply the determinant of A, the matrix up here, minus lambda times I. So to be explicit, I want to compute this determinant here. So that's not bad to compute, right? If I take the difference of these two matrices, I simply notice that this is just going to be the determinant of this quantity here, right? I just subtract these lambdas off the diagonal, and that's what I want to find the determinant of. So here I need to decide how am I going to find this determinant. Do I want to take the determinant of this vector as is, or do I want to do some elementary row operations to first simplify the matrix a little bit? Well, if I just look at the first row, I can notice I have a non-zero term with two zero terms. That makes computing this determinant rather easy as is, so let's just do a cofactor expansion along this first row here. Okay, so if I do that, I'm going to get a plus times this term here, multiplied by the determinant of, well, I would ignore this row and this column, so just this determinant here. So if I want to be explicit, this first simplifies to this determinant like so. Okay, so from here, just to be explicit, notice that the second two terms that I would technically need to compute this determinant are just 0 multiplied by some determinant and 0 multiplied by another determinant, so I can just neglect those two terms directly. Okay, so now I want to compute the determinant of this 2 by 2. Well, that's just simple, right? I take this product minus that product there. So upon doing this, I simply get this expression here. Okay, so now I simply want to simplify this term here to see what it becomes. Well, I can simply distribute this lambda through and then add it to whatever that term is. After I do this, this is the expression that I end up finding. So to be explicit, this term here is simply the term that I had in these square brackets over here. Okay, so now since I'm kind of wrote all this stuff out here, if this was my write-up for a problem, I should say what I just did, right? So I could say explicitly here, I expanded along the top row when evaluating the determinant of the 3 by 3 matrix. This just makes it clear to whoever reads your work what you did. Okay, so now my next goal when trying to find these eigenvalues is to simply find the roots of this characteristic polynomial. So we can just simply note, hey, this is a third degree characteristic polynomial, therefore there will be exactly 3 roots up to multiplicity. So just kind of looking at this, I can immediately tell one root is just going to be 2 from here. So explicitly, I could state something like, clearly, lambda 1 is equal to 2 is an eigenvalue. Next, I need to solve this quadratic here. Well, lucky for us, we have the handy-dandy quadratic formula. So I could say to find the other 2 eigenvalues, we simply note that the roots of that polynomial will be equal to what? Well, these things are going to come in these conjugate pairs of plus or minus, and it's going to simply be the terms given by this quadratic formula here. Okay, so I labeled these lambda plus and lambda minus just for convenience to differentiate via this plus and minus here. So if you just do some classic stuff that you've done multiple times before, you can find these roots and you'll simply get that lambda plus is negative 3 plus 3j and lambda minus is negative 3 minus 3j. Okay, so to be explicit, you can say, thus the other 2 eigenvectors are these guys here. Okay, so now I have 3 eigenvectors, right? I have this term, and this term, which is exactly what I knew should happen, given the fact that this was a third degree polynomial. So I have all of them. So now my goal is to simply find the eigenvectors that are associated with each one of these eigenvalues. So in particular, I want to find a eigenvector for each eigenvalue. Okay, so let's just do this lambda 1 is equal to 1 first. So how do we go about doing this? Well, recall that the eigenspace for any particular eigenvalue is simply given by this null space of A minus eigenvalue times I. So I need to compute the null space of A minus 2I. Okay, how do I do this? Well, we've done this before, right? We simply row reduce A minus 2I. So let's see what that would look like. Well, first I need to figure out what A minus 2I is. So if I go back up here, this is my matrix A, and I want to subtract 2 from the diagonal. The rest of the terms will stay the same. So I'll get 2 minus 2, 0, 0 minus 2, negative 2, and negative 6 minus 2, negative 8. So if I put all these together, my A minus 2I is simply this quantity here. Now I want to go through the process of row reducing this. So the first thing I can note is, hey, I usually like to have my pivot point at the top, so let's do this. So here I could simply do these two row swapping operations, basically putting this row at the top and putting this row in the middle. So after I do that, this simply becomes this matrix here. Okay, next I can notice this is a 2, this is a negative 2, and this is a negative 6. I can divide everything here by 2 and end up with integers. That's the reason why I picked the middle row to go to the top row. Okay, so from here I can simply do that process by simply computing this term here for the top row. Next, just to save a little bit of time in doing this computation, you can notice the middle row. Hey, if I just take the middle row and subtract the top row from it, I get a 0 in this position. I want that to happen, so let's just do both of these operations at the same time. So you can do this because I'm using the old row here, and it's a valid way of doing this, a bit quicker. So from here, if I divide the top row by 1/2, I'm simply going to get 1, negative 1, 3. And for the next term, if I take 2 minus 2, I get 0. 3 minus negative 2, I get 5. And negative 8 minus negative 6, I get my 2 here. Okay, so from here, the next thing I want to do is turn this 5 into a 1. Well, how can I do that? I could simply take the second row and divide by 5. So if I do this, this is the quantity that I get here. Finally, I want this negative 1 to be a 0 to have everything in RREF form. So I can do that by adding the first row to the second row. So doing this gives me my reduced row echelon form here. So from here, my goal is to find the null space using this matrix. Well, that's pretty trivial, right? So if you look at this column, that is my only column that doesn't have a pivot. Therefore, this will give me a free parameter for my x sub 3 term. So from there, I can simply solve for x sub 1 and x sub 2. And once I do that, I get that the null space will simply be this collection of vectors here. Okay, so the null space will be all vectors of this form for any value of t. Okay, so if I want to pick a particular eigenvector for this eigenvalue lambda 1 is equal to 2, all I need to do is pick some value of t different from 0 and plug it into here, and I get my vector. Well, here you can kind of notice that, hey, if I plug in 5, if I choose t is equal to 5, nice things happen, right? I get the 5 cancels this 5, and that 5 will cancel this 5. So I end up with nice integers. So from here, I'm going to choose to do this, and I'll say that my eigenvector for lambda 1 is equal to 2 is simply going to be this negative 17 to 5. Okay, again, this is a choice. You could have picked any other value of t other than 0, and you get a valid eigenvector. Okay, so next up, I need to compute the eigenvectors that correspond to my eigenvalues of negative 3 plus 3j and negative 3 minus 3j. Okay, so it could be tedious doing both of these one at a time, and you can notice I have kind of a way to do a shortcut here. I have this plus or minus thing going on, right? So what I could simply do is find the eigenvectors for each of these eigenvalues at the same time by utilizing the fact that lambda 2 and lambda 3 are really just these two things here. One comes from the plus, one comes from the minus. So I'm going to utilize this, and I'm going to compute the null space of A minus this quantity here times I to find both of these eigenvectors at the same time. Okay, so I now want to row reduce this term here. So first notice, if I distribute this -1, I get 3 plus 3 minus plus 3j all times I. So this quantity here explicitly. This is the matrix I now want to work with. Well, let's just plug it in. So if I go back up here and take everything on the diagonal and I add this 3 minus plus 3j, I simply get a new matrix that will be given by this term here. And my goal is to row reduce this matrix. Okay, so going about this, well, this term here is what I ultimately want to turn into one of my pivots. So I can simply turn this into a 1 by dividing by this quantity here, this 5 minus plus 3j. Okay, if I do this, these other two terms, since they were zeros, stay as zeros. So here, dividing by this doesn't introduce any complications in simplifying things. Okay, now my next goal is to use this top row to turn both of these two 2's into a 0. Well, that's a pretty straightforward operation. All I have to do here is simply take this transform here. I take this row and subtract 2 times the first row, and this row subtract 2 times the top row. Okay, that just gets me this here. Okay, next, I want to be a little bit cautious here. I could just divide this row by this complex term here, but dividing by complex numbers is kind of a pain compared to dividing by real numbers. So I could simply notice, hey, down here, this is just a 3. Why don't I swap rows and work with the 3 instead of this complex term? Okay, so if I do that, it'll save myself quite a bit of work and make the computations a little bit easier. So let's just swap row 2 with row 3 to get this. Okay, now if I divide this term by 3, everything works out pretty nicely. So I'm going to replace row 2 with 1/3 of row 2. Doing that gives me this quantity here, 1, and this quantity, -1 minus plus j. Okay, that's pretty nice and easy. So now I need to use this 1 to get rid of this term here. Well, sadly, I'm kind of stuck multiplying by complex numbers. So the way that I would do this is I'd take this row and I'd multiply it by 3 minus plus 3j, and I would add it to this. So to be explicit, the row operation that I'm going to do is this term here. Okay, by doing this, I have to take this quantity and multiply it by this thing here. It's not too bad, so let's just kind of write that out and see what it looks like. Well, that would row reduce to simply this matrix here. Okay, so here, this becomes a 0, since that's the way that I picked this row operation, and the other term becomes -6 minus this thing times this thing, which I just left as this, but that simplifies to -6. Okay, so just a little bit of complex arithmetic review there. Okay, so from here, since this is simply just a -6, 6 minus -6, that thing is just 0. So this matrix directly simplifies to, by doing that simplification, this term here. Okay, this is now an RREF form. Okay, so from here you can say, hey, what's my free parameter? Well, my free parameter is associated with this column. Let's introduce that to be t. So if my x3 is equal to t, then my x1 would just be 0, and my x2 would just be negative of this. So if I put all of that together, my null space will simply be the collection of all vectors of this form here. Okay, these guys here, 0, my negative this thing times t, and just t. Okay, so now I want to pick a value for t. Again, it doesn't matter what I pick as long as it's not 0. Let's just pick t is equal to 1. Why 1? Well, here I just get nice 1s everywhere, and that's pretty nice, so it's kind of convenient. So if I choose t is equal to 1, then I can pull out my 2 eigenvectors for my different eigenvalues. So recall that my lambda 2 was my +1, and the lambda 3 was the -1. So from here, if I put the plus, I get my lambda 2. are the eigenvector associated with lambda 2. So there I would just get this. And if I plug in the t is equal to 1 and take the -1 root, I simply get an eigenvector associated with my eigenvalue lambda 3, or just this term here. Okay, so this is a nice little shortcut if you are going to try to compute eigenvectors for eigenvalues that are conjugates of each other. So just kind of keep this in mind. You don't have to do it if the plus minus plus thing gets confusing. And if you do it, make sure you're very cautious with keeping track of which sign is which. Okay, so to summarize and put everything together, I have kind of three cases. So here, if lambda was 2, I got this eigenvector. And if my lambda was equal to my -3 plus 3j, I get this eigenvector. And finally, if lambda is 3 minus 3j, I get this eigenvector. So it's a good idea to just kind of put all this together as a concluding statement for your proof. So something like this, to summarize, the eigenvalues are this, 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 and an eigenvector for each one of these is this, this, this. Make sure to always say an eigenvector because there's infinitely many of them. So that's it for question 1. So now let's look at question 2. So if I wipe all that out, question 2 asks me to diagonalize this matrix. So in a question like this, we're kind of telling you that the matrix is diagonalizable since we're giving you a command to do it, but you should mention why the matrix is diagonalizable somewhere in your work, because I could tell you to do something and it's not possible. Okay, so before actually looking into this question, let's shed a little bit of light about how diagonalization works by giving a slightly different way of viewing diagonalization than the way that was in the notes. And in this process, we'll kind of motivate why you even might want to do something like this. If you want to skip this discussion and go straight into the process of diagonalizing this matrix, then just go to the time marker that is posted on the screen now. Okay, so here is my tutorial. So first of all, you do have until December 5th to fill out the Evaluate survey. Do it from Army. But suppose A is a diagonal matrix. So rather than saying, like, let's do something to make it diagonal, let's just say, what if it is? What happens, or what nice things occur if it's diagonal? Well, it turns out that lots of computations become quite a bit easier. So for instance, if I want to take A times a vector x, where x is just this x1 up to xn, if A is a diagonal matrix, then this product is simply just scaling each one of these terms, right? Just a11x1 up to annxn. You don't have to do that thing where you add the terms together. So if you're doing this in a computer, that's less computations, which is very good, faster runtime. Next, what if I want to solve a system? What if I want to solve ax is equal to b, where here I'm kind of assuming that this system is consistent? Well, if each one of these terms is non-zero, then I can immediately find a solution by saying, hey, the solution x is just going to be b1 divided by a11 for the first term, all the way up to bn divided by ann for the nth term. Again, this is assuming that aii is non-zero. If, on the other hand, one of these ii terms was equal to 0, then you need the corresponding b term to be 0, and that would just give you a free variable for x. So in either case, this is very easy to solve this system. Okay, next up, what if I wanted to compute a to the n? So we've seen some applications where we wanted to compute a to the n for some of the graph theory stuff, right? Well, here it turns out that if I have a that looks just like this, if I want to compute a to the n, that's simply taking the nth power of each of these diagonal terms. Okay, so in general, if I can make any given matrix a diagonal matrix, then life is good and computations are significantly faster to do. Computers really rely on being able to diagonalize things to make things really nice. And when you can't, then things are quite slow in comparison. Okay, so let's just kind of start out with an assumption here. What if some n by n matrix A has these eigenvalues lambda 1 up to lambda n, with corresponding eigenvectors v1 to vn being such that this collection of all the eigenvectors is a basis for Rn. So kind of note here, these lambdas need not necessarily be distinct, but I do need to have this basis here for all of the stuff that I'm going to do to hold? Well, let's find out what happens. So here, if x is an Rn, then since this b is a basis for Rn, I know that I can write x as a linear combination of the bases elements. So explicitly, x is equal to b1 x1 plus da-da-da-da up to bn vn. Okay, so from here, thus, I can rewrite x as a matrix vector multiplication as such. So here, all I'm really doing is noticing that, hey, if I do this matrix vector multiplication, then the first term of the resulting vector would be v11, b1, v22, b2, all the way up to vnn, bn, which is exactly what I get here. Okay, so this is just a different way of writing x. So from here, this lets me actually compute how to find these b coefficients. All I do is take p inverse times x. So from here, this kind of begs the question, why is p invertible? Well, in general, this system is going to be consistent because I know there's a solution, thus p has to be invertible. Or another way of thinking about it, I could simply say, hey, this thing is a basis, so if I were to row reduce this thing here, I would get that the rank is simply n, therefore p is invertible. Lots of different ways of thinking of why this has to be invertible. Okay, so now that I've done all of this stuff, let's consider a times this vector x. Well, I know x can be written in this basis here, so let's just do that substitution. So x is just this. So now I know A is a matrix, therefore I can split this up by using the linearity of A. That would simply be b1a v1 plus all the way up to bn a vn. Okay, now what do I know about a v1? Well, v1's an eigenvector, and the eigenvalue for this eigenvector is lambda 1. So a times vi will simply be lambda I vi. So doing this replacement gives me this here. Okay, now let's do the same trick that I did up here to switch from this equation to this equation. Here I have all these vectors here tied to it. Let's factor those out and recover this p matrix. So doing this gives me that this term simply becomes this here. So it's kind of the analog of this, but instead of having b1 through bn, I have b1 lambda 1 through bn lambda n. Okay, so from here, what do I do next? Well, you can notice that I have these lambdas here, so I could rewrite this matrix as a vector times a matrix. So the vector I'm going to have will simply have these lambdas along the diagonal and zeros everywhere else, and this would just be multiplied by the b vector. Okay, now here I had a times x, so ultimately it'd be nice if I could write this as a bunch of matrices times x over here. Well, I can do that, right? B is just p inverse times x. So I could rewrite this as p inverse times x, and now I have a equality across two matrices. So to be explicit with my last statement, I simply have a times x is equal to this matrix times x, where I call this thing p, this thing d, and this thing p inverse. So this big matrix. Well, if matrix x is equal to matrix x for every x in the real numbers, that means that the two matrices are equal. So here I get A is equal to P, D, P inverse. Okay, so this thing is not diagonal, but it's almost diagonal, right? I have this P and this P inverse to deal with. So I still maintain a lot of those computational benefits of getting a diagonal matrix, but I just have to multiply by P and this P inverse first. Okay, so before we go on, let's notice something here. If T sub A is the linear transform with the standard matrix of A, then I can build another matrix representation of T sub A. So explicitly, I can talk about the matrix of T sub A with respect to the basis B, where this was just my collection of all the eigenvectors. So this, by definition, is just going to be this quantity here. Notice this is similar to what we had before when we found the standard matrix, other than now I'm using V1 through Vn. So if I do this, then the matrix here, this matrix, is exactly a diagonal matrix. Okay? The downside of doing this is here my matrix is acting on vectors written in the bases B instead of my standard bases. So I could rewrite this matrix A as being a perfectly diagonal matrix if I change the bases to act on the eigenvectors instead of the standard bases. It's a different matrix, so you can't say A is equal to this. It's not true. A is equal to this thing here. But what this matrix here and this matrix here are doing is really just changing the bases for the representation of the matrix for the linear transform T sub A. So yeah, it's kind of beyond the scope of the class, but not so much, but you won't be tested on this directly. But I just wanted to mention that this is a thing you could do to make it perfectly diagonal. Okay, so let's continue from here by discussing some of the theorems in the course notes that we will use. So, definition 42.5, this introduces the definition of a diagonalizable matrix. So here, A is diagonalizable if there exists this invertible matrix P, such that this thing is true here for some diagonal matrix D. Okay. Next up, this lemma is quite useful. So it tells me that if A is an n by n matrix with these being distinct eigenvalues of A, then further, if B is going to be a basis for these eigenspaces for I ranging from 1 up to k, then if I take the union of all these bases, that gives me a linearly independent set. So essentially, the union of bases from different eigenspaces is a basis for something. If it so turns out that it's a basis for Rn, then all of the stuff that I did before on the previous slide works, and I can diagonalize A. Next up, we have an important theorem, the diagonalization theorem. An n by n matrix A is diagonalizable if and only if there exists a basis in Rn consisting of eigenvectors A. So essentially, the work that I did before gives a proof that if it has a basis consisting of eigenvectors, then it is diagonalizable. There's the other proof in the course notes that you should, of course, be familiar with. So finally, we have these two corollaries, which will be very useful in practice, and we will apply it to the problem that we introduced before I got into my lecture slide discussion. Corollary 42.10, an n by n matrix A is diagonalizable if and only if the geometric multiplicity equals the algebraic multiplicity for every eigenvalue. And another corollary, 42.11, if an n by n matrix A has indistinct eigenvalues, then it is diagonalizable. So generally speaking, if I want to show that something's diagonalizable, I will use one of these two theorems, and you should mention them for any problem where you're diagonalizing a matrix, just to justify why you can diagonalize it. Okay, all of this said, let's go back to that problem that I mentioned previously. Okay, so from the theorems I just discussed, if I want to diagonalize this matrix, I first need to find the eigenvalues and an eigenvector for each one of these eigenvalues to see if we could diagonalize this. Okay, so if I want to find the eigenvalues and eigenvectors associated with those eigenvalues, I first need to find the characteristic polynomial. Well, how do I do this? Well, the characteristic polynomial is simply the determinant of A minus lambda I. So in this case, if I subtract lambda from the diagonal, it's this determinant here. Okay, so in expanding this determinant, you can notice, hey, I have a 0 here and a 0 here. So let's just use this last row to make doing this quite easy. So if I do this, the first expansion tells me that the determinant will simply need to be this term here, this 4 minus lambda, multiplied by the determinant of this 2 by 2. Okay, so if I do that, determinant of a 2 by 2, that's trivial to compute. It'll simply be this term multiplied by this term minus the 2 times 0, or simply the product of these two terms. Okay, so from here, that is my characteristic polynomial, and lucky for me, it is already in factored form. So if I look at this, what are the roots? Well, that's simply going to be 2, 3, and 4. And from there, each one of the eigenvalues would simply be lambda is equal to 2, lambda is equal to 3, and lambda is equal to 4. Okay, clearly, either from this equation or from noting that it's a 3 by 3 matrix, so it has at most 3 eigenvalues, you notice that clearly each one of these eigenvalues has an algebraic multiplicity of 1. So from here, if I go back to this theorem, I could apply this corollary 42.11. Here I have indistinct eigenvalues, therefore A will be diagonalizable. So I could conclude here that it is diagonalizable. Okay, so now I go through the process of finding the eigenvectors, or a eigenvector, for each one of these eigenvalues. Okay, so I do this one at a time. So for lambda 1 is equal to 2, I simply need to compute the null space of a minus 2I. And again, just recall, I do this by row reducing a minus 2I. Okay, so here, to do that, I simply write the matrix a minus 2I. That simply subtracts 2 from the diagonal, so if I plug in 2 for each one of these, this is what I get here, right? 3 minus 2 is 1, 2 minus 2 is 0, 4 minus 2 is 2. Now I want to row reduce this guy. Well, the first thing I can notice is, hey, I already have a pivot here in the spot that I want it to be, and thus I just want to simplify these last terms here. So I'm just going to take the path where I divide R3 by 1/2 to turn the 2 into my next pivot. And now let's use this new 1 to get rid of the terms above it. Well, to do that, it's just two simple row operations, right? R1 plus 4R3 and R2 plus 2R4 R3. And finally, I want to put this pivot in the correct location, so I swap rows 2 and 3. You could, of course, here have turned row 2 into the pivot and canceled things out there. Multiple ways of doing the same problem. Okay, so from here I want to read off what the null space is. Notice I have one free parameter, this term here. And kind of notice I only can have one free parameter since the algebraic multiplicity of each of these eigenvalues is 1, and that is an upper bound for the geometric multiplicity. Therefore, I really have to have exactly one free parameter if I didn't make a mistake. So you could use that as a sanity check here to make sure that you're doing the correct steps. Okay, so from here, I can simply compute the null space by introducing a free parameter for this column here. And when I do that, I get that the null space is simply this collection here. Okay, so if I want to find an eigenvector for this particular eigenvalue, I can pick any value of t other than 0, and I am just going to pick t is equal to 1, just because it gives me nice integers, and conclude that this thing is an eigenvector corresponding to the eigenvalue here. Okay, so next I repeat the same step, and just to not rehash everything in such a great detail, let's just copy paste here. So for lambda 2 is equal to 3, I want to compute this null space, right? I just replaced this thing with a 3, and thus I want to row reduce this. So from here, if I plug in 3 into this expression up here, I get 0, -1, 1, so the number's here, and then I want to row reduce. How do I do this? Well, here I can turn this into my leading 1, so divide it by 2, that's all nice. Here I can get rid of this term here, or the -1 here, by doing this row operation, and after I do that, this is what I get. Next, I can use the 1 at the bottom to get rid of these two terms here by doing these row operations like that, and then I can swap rows again to get this. Okay, so from here, you can notice, hey, my only column without a pivot is simply this term here. Therefore, I will have a free parameter associated with x1. So from here, x2 is 0 and x3 is 0. Therefore, the null space is the collection of all of these vectors. Again, I have my choice for a value of t to pick out a particular eigenvector, and I'm just going to pick t is equal to 1, and this gives me this eigenvector here for this eigenvalue. Okay, so now I have to do this yet one more time for the eigenvalue lambda 3 is equal to 4. So doing this, here's my work. So for this, I want to compute this null space. So I row reduce this, and from here, all I do is my standard row reduction stuff. So after I plug in -4, I get my -1, my -2, and my 0. So these terms here. I want to turn this into a 1, so multiply by -1. Next, I note that this term here can be turned into a pivot. So since this is just a -2 as well, let's use this row to cancel out the terms over here. So I can do that just by subtracting row 2 from row 1, and that would give me this term here. And finally, to turn the -2 here into a pivot, I divide by -2, giving this matrix here. Okay, so from here, my row without a free parameter is this third term here. So I'm going to get a free parameter associated with x3. So doing that and calling it t, I simply get that the null space is this collection here. Again, I can pick any value of t that I want other than 0 to get an eigenvector, so let's just use 1 because integers are nice. So if I do this, this is an eigenvector corresponding to this eigenvalue, lambda 3 is equal to 2. Okay, so fixing up a few of those little typos here, lambda 3 is 4, lambda 2 is 3, and that one was correct. Let's go on from here. So before I actually diagonalize A, I need to do the thing where I justify that I can diagonalize it, right? I could have done it up here, where I simply noted, hey, corollary 42.11 applies. But instead, let's use corollary 42.10 just to show how one would use that corollary. Okay, so from here you could say, hey, the bases for e sub lambda I of A for each one of these i's equal to 1, 2, 3 all contain one vector, right? A basis for each one of these null spaces is simply the vector that I picked here to be the eigenvector of them, right? This one, and this one respectively. Thus, the geometric multiplicity for each one of these eigenvalues is equal to 1. And this, of course, is the same thing as the algebraic multiplicity. Thus, I could apply corollary 42.10 as well as corollary 42.11 to show that this is diagonalizable. So further, I know that my P matrix is simply going to be the matrix of all the eigenvectors. Okay, so here I can just throw my eigenvectors in any order that I want. Here I picked my V1, this term here, followed by my V2, this vector here, and then my V3, this vector here. But again, the order doesn't matter. It does change the order of the D matrix, though. So now, before we discuss the D matrix, let's actually compute the inverse of the P matrix. So here's all the stuff I need to do. Basically apply the matrix inversion algorithm, or you could do the things with the adjoint and the determinant if you will. It's your choice. So here I put my P matrix here, I put my identity matrix here, and I row reduce. So here you can notice, hey, I already have a 1, so let's just swap rows so my 1's in the nice position. So after I do this, let's use the top row to get rid of this thing here. So to do this, I simply do this row operation here. And then next, I now have my nice diagonals here. I need to get rid of the negative 12 and the negative 2, and that's just these simple operations here. So after doing all of these things here, you can notice that the inverse of P would simply be this matrix here. Okay, so putting all this together, I now have that A can be diagonalized as P, so my first matrix over here, this P matrix, times my D matrix. Well, how do I find the D matrix? Well, the eigenvalues that I put on these diagonals will simply be the eigenvalues that correspond to the eigenvector of that column. Okay, so the eigenvalue for this eigenvector was 2, the eigenvalue for this one was 3, and the eigenvalue for this one was 4, thus 2, 3, 4. And finally, the matrix that goes over here is my P inverse. Okay, so this is how this matrix A would diagonalize. And that is it for question 2. So we delete everything here, and now we look at question 3. Okay, if A is this, compute A to the 5th. So in this case, you could try to take this matrix and multiply by itself 5 times. It's just a 2 by 2, it's not too bad, but if this was a 10 million by 10 million, you definitely wouldn't want to do this. You'd want a faster way if possible. Well, it turns out that if A is diagonalizable, then taking A to the 5th power is really easy. So let's try to diagonalize A. Well, if I want to diagonalize A, I first need to find its eigenvalues, and I'm going to hope that I can find a basis of its eigenvectors after I find them. Okay, so to find the eigenvalues, I compute the roots of the characteristic polynomial. So just throwing all of this material up here, method 1, I could simply say, hey, the characteristic polynomial is simply this determinant where I subtract off the lambda off the diagonals. This is a 2 by 2 determinant, so it's just the product of this minus the product of that, so this thing minus 9. That can be simply simplified by expanding out this term here and adding in the 9 to get this thing here. Okay, so from here I can factor this into this term times this term. So from here I can say, hey, the roots of this are going to simply be minus 1 and 5. Thus the eigenvalues will simply be negative 1 or 5. So Since we've recently introduced the idea of the trace, and we've talked about the determinant being the product of the eigenvalues and the trace being the sum of the eigenvalues, let's show a different method that you could use to find the characteristic polynomial of a 2 by 2. This method can be generalized for higher sized matrices, but it's most useful for a 2 by 2. Okay, so from here, let's just notice, hey, if lambda 1 and lambda 2 are the eigenvalues of A, then the product here is simply going to be the determinant of A. Okay, and I can compute the determinant of A. That's just 2 times 2 minus 3 times 3, this quantity here, and that's just simply minus 5. So from here, I know that the product of the eigenvalues is negative 5. Next, I know the trace is just the sum of the eigenvalues, so lambda 1 plus lambda 2 is the trace, but this is the same thing as the sum of the diagonal entries of A. So the trace is 2 by 2 plus 2, or simply 4. So here I know lambda 1 plus lambda 2 is equal to 4. This gives me two equations, the first one here and the second one here, that I can try to use to solve for lambda 1 and lambda 2. So let's do this. From the trace equation, I know lambda 1 is simply going to be equal to 4 minus lambda 2. Okay, if I use this in the determinant equation, I simply get negative 5. The term over here is lambda 1 times lambda 2, this thing. But lambda 1, the quantity here, is just 4 minus lambda 2. So this is 4 minus lambda 2 times lambda 2. Well, I can expand this thing out, and I get this quantity here. Lo and behold, this is exactly the characteristic polynomial I had up here. Okay, so from here I can simply note, hey, this thing's a root, and the other root's negative 1. So if I take these solutions and plug them into the trace formula, from there I can say lambda 1 is equal to negative 1, or the other corresponding root, if I had lambda 2 is equal to negative 1, is just 5. So this just gives you a novel way of computing the eigenvalues if you so choose to use it. Okay, so in either case, it's pretty clear that these eigenvalues have multiplicity 1, namely they're only a root once from here, or namely there's two eigenvalues and I have at most two eigenvalues, therefore they can't have any other algebraic multiplicity. And we now find the eigenvectors corresponding to these. So from here we could have, if we wanted, applied that corollary 42.11 to conclude that A is diagonalizable at this point. But again, it doesn't matter if we do it here or at the end, we just have to do it at some point. Okay, so to find the eigenvalues for this, I simply compute this null space. Well, A plus I is just this. Simple row reduction gives me this. Here, my free parameter is associated with the second column, and from here, I simply get the null space is all vectors of the form negative tt for t is in R. So that's my eigenspace. So from here, I simply choose t is equal to 1 to get that this is an eigenvector corresponding to this eigenvalue. So for lambda 2 is equal to 5, I do the same thing. I compute this null space, I row reduce this. Once I plug in this, that's my matrix. You can see pretty clearly under these two operations here, that is what this row reduces to. So here I get a free parameter for here, and my null space would simply be all matrices, all vectors of the form tt, where t is a real number. Okay, and again, I can just choose t is equal to 1. Any number other than 0 works. And thus I can see that this is going to be an eigenvector corresponding to lambda 2 is equal to 5. Okay, so now is at the point where I really need to mention that A is diagonalizable by either appealing to corollary 42.11 and using the fact that I have distinct eigenvalues, well, two distinct eigenvalues for a 2 by 2 matrix, or I can do the same thing that I did previously and apply to corollary 42.10 by simply noticing that the bases for each one of these eigenspaces all contain one vector, and thus each one of these eigenvalues has a geometric multiplicity of 1. That's the same as its algebraic multiplicity. Therefore, A is diagonalizable by corollary 42.10. Okay, so your choice there. So now I want to figure out what my P matrix is, what my P inverse matrix is, and what my D is. Well, to find P, I simply take my eigenvectors and throw them into a matrix. So here I just chose to put the eigenvector associated with -1 and an eigenvector associated with 5 in that order. Next, I want to find what my P inverse is. Well, this is simply a 2 by 2, so I can use that handy-dandy formula using the adjugate to make this pretty easy to compute. So here, the determinant of p, well, negative 1 times 1 minus 1 times 1, just negative 2. And the adjugate, well, I flip these two terms, so I get, so I flip these two terms, so I get 1, negative 1 here, and I negate the terms off the off diagonals, giving me negative 1 and negative 1. So using the fact that P inverse is 1 over the determinant times the adjugate, it's simply this product or this single matrix here. Okay, all that is left to diagonalize the matrix A is simply to put all of this stuff together. So from here, A is simply going to be P times D times P inverse. So here, this is going to be my matrix P here that I grabbed from here. This matrix D, well, that's going to be the matrix of the eigenvalues associated with these eigenvectors. So lambda 1, lambda 2, so negative 1, 5, sitting there. And finally, my P inverse. Okay, so now I've diagonalized A, but how does that help me compute A to the 5th? Well, let's just kind of examine this for a second. So A to the 5th, that's going to be the same thing as P times D times P inverse to the 5th. So if I were to write this out, this is going to be P times D times P inverse multiplied by itself 5 times. So let's just write this out very quickly through the magic of copy paste. So 1, 2, 3, 4, 5. So this makes it really clear what the pattern is. I can regroup matrix multiplication in any way I want. So I could regroup this so that this term is grouped with this term here. This is just the identity matrix. I can do the same thing here. This is the identity matrix. The same thing here, and the same thing here. So if I put all these together, all of these things become identity matrices, and all that I'm left with is P times D times D times D times D times D, that's just D to the 5th, times P inverse. Okay, this works in general. Okay, so chasing that out, now all I have to do if I want to compute A to the 5th is to compute D to the 5th, multiply it by P on the left-hand side, and multiply it by P inverse on the right-hand side. Well, this thing is a diagonal matrix. So if I want to take a diagonal matrix to the 5th power, all I have to do is take the elements on the diagonal and raise them to the 5th power. So doing this gives me this quantity here. Okay, so negative 1 to the 5th is negative 1, 5 to the 5th is this quantity. Okay, now I just have to multiply by P and P inverse. Doesn't matter if I multiply these ones here first, so if I put parentheses here, or if I multiply on the other side first, so if I put parentheses here. It's your choice. You get the same thing either way. I just chose to multiply on these two here first, and then the other one. So if I do that, this product of these two matrices is this, and then the product of these two matrices is this. So from here, I simply get that A to the 5th is equal to this matrix here, and I'm done. So again, this is just a square matrix. It's not too terrible computing this thing to the 5th on its own. And you could argue that it could be easier to compute A to the 5th on its own rather than doing all this work here where I compute the eigenvalues. But if A was a really big matrix, or if I wanted to take A to a really large power like 9001 for a nice meme number there, then this method would definitely be easier by hand, and it's actually easier to do in a computer as well. Okay, so that is everything for question 3. Let's go on to question 4. So for question 4, we're changing our space a little bit, our problems that we're talking about a little bit, and we're talking about abstract vector spaces. So briefly before we get to this question, and if you want to skip this discussion and go directly to solving this question, just simply go to the time marker that's appearing on the screen now. But before getting into the details of solving this particular problem, let's briefly discuss abstract vector spaces in a little bit of detail to say, what do we actually mean by all of this stuff? Okay, so if you recall previously, we had a definition that looked really similar to this definition, but instead of saying V, we talked about Rn. Well, it turns out that there's lots of objects that satisfy all 10 of these properties that are satisfied by vectors in Rn, and those objects are very interesting to study in and of themselves. For instance, polynomials can satisfy this. The set of all matrices can, or the set of all n by n matrices can satisfy this. There's lots of interesting sets that satisfy this. So we're taking the idea of a vector in Rn, and we're now talking about vectors in different objects. Okay? And we call this whole thing an abstract vector space. So with this in mind, most of the work that we've done before comes back up and generalizes exactly as you would kind of expect it to. So we can talk about linear independence, subspaces, all of that stuff. So here, just kind of key definitions. Span, that's a thing. Linear combination, that's a thing. Linear dependence, linearly independence, that's a thing. Nothing really changes other than the types of objects we're dealing with. So instead of these being vectors in Rn, these could be polynomials or matrices or functions or all kinds of things. Same thing for a subspace. So a subspace is simply a subset of V that satisfies all of these properties. And again, the subspace test comes back in for the exact reasons why it worked for Rn. So all of this work we've spent so much time developing in this course for Rn holds for many, many other very important objects. And these have applications to things like solving partial difference equations, talking about the shapes of atomic orbitals. All of this stuff has applications there. So just if you're ever in doubt of if you can do something for an abstract vector space C or V, just think if you could do it for Rn, you can probably do it for V. You just have to think of how it generalizes appropriately. And most of the generalizations are mentioned here in these definitions. So definitely make sure you know the definitions, but let's get into a particular example to kind of flex these definitions a little bit. So here I'm given a set S, and it's just the set of all these rotation matrices, and I'm asked to determine if this is a subspace of the set of all of these matrices here. So notice this thing forms a vector space since it satisfies the 10 axioms that I had there. So there's two solutions that you can really do from here, or you can combine them to make one kind of solution that really drives the point home. So for the first solution, we're simply going to notice, hey, there's no theta in R such that all four of these terms are simultaneously zero. Well, that means that the zero matrix is not an S. If this thing doesn't have the zero matrix, then it can't be a subspace of M 2 by 2 of R. That's one counterexample. There's one solution. Another solution that you can do is to attack scalar multiplication. So in some sense, this also is attacking zero, so it's kind of the more general solution. Note that for any S or any A in S, 0 times A is the zero matrix, which again is not an S. Thus, S is not going to be closed under scalar multiplication, and hence is not a subspace of M2 cross 2 of R. Okay, so that is it for question 4. Pretty straight and to the point. So let's look at question 5. So here I have a little bit of flavor text for it. In many real-world applications, the standard bases for the vector space of nth order polynomials, namely this basis here, is not the most convenient bases. In particular, when, say, solving differential equations and that type of stuff that you'll do in the future, you'll want to have a different bases of polynomials in order to get clean solutions and to be able to even solve some problems. Okay. One useful basis of polynomials consists of these Legendre polynomials, so these L sub n of x's that are defined in closed form by this summation here. So again, these polynomials actually come from an application of linear algebra to solving differential equations. So hopefully you'll see that in one of your future classes. I know a couple of the sections do. I'm not sure about all of them though. Okay, so to be concrete, the first 4 Legendre polynomials are given by this here. So if you plug in the values for n here and compute these terms, the first one, if you do n is equal to 0, is this. If you plug n is equal to 1, you get a sum, and that sum just simplifies to x. If you plug in 2, the sum simplifies to this, and if you plug in 3, the sum simplifies to this. So here we're asked to prove that this set L, consisting of Legendre polynomials 0 up to the third one, is a basis for the vector space of third degree polynomials P3. Okay, so if I want to show that something is a basis for a vector space, just because it's an abstract vector space, it doesn't really change the process. So the first thing I need to do is show that L is a linear independent spanning set for P sub 3. So to show it's a basis, it's still a linearly independent spanning set. Okay, so here let's just show that it's a linear independent set first. So to show that L is a linear independent set, I need to find solutions to arbitrary linear combination of the basis elements is equal to 0. So to be explicit, this thing here, C1, C2, C3, C4, are just going to be real numbers. I want to find a solution to this. Okay, so from here, this is just a big polynomial over here, right? So I can simplify this by combining the various terms to write it in kind of the standard form for a polynomial. So to be explicit, I can note, hey, this x to the third term, it only comes from this bit here, so that's the power of x to the third. The x squared terms, I have a little bit of this term here, and I have a little bit of this term over here for, nope, just this term. Okay, and then for the x term, I have some stuff here and some stuff here to combine over there. And for the constant term, it's just this plus that term here. Okay, so I have a polynomial is equal to 0. Well, two polynomials are equal precisely when their coefficients are equal, right? So from here, since two polynomials are equal exactly when their coefficients are equal, this above equation is simply equivalent to, well, coefficient set it equal to 0, coefficient set it equal to 0, this is equal to 0, and that is equal to 0. So I can clean this up and make it look a bit nicer. This term here just becomes this equation, this term gives me this equation, and these two terms give me these two equations. Okay, so my goal is to show that the only solution to this is when C1 is equal to C2 is equal to C3 is equal to C4 are all equal to 0. If I can show that, then I know this is linearly independent. So from here, let's just kind of chase this out. You could do this by putting it in a matrix and simplifying it, but this system is simple enough that you could just read it off, right? Here, I know this equation tells me C4 is 0, and this equation tells me C3 is 0. So explicitly, from the last two equations, we have this statement here. Okay, now if I plug these into the first two equations, it gives me that is a 0, and this is a 0. Well, that directly tells me that C1 is equal to C2 is equal to 0. Okay, so from here, I know this is the only solution. There's no other way that I could go through this process. If you really wanted, you could put this into a matrix and say, oh, it has full rank, therefore there's a unique solution. And since there's a unique solution, and since 0 is the trivial solution, is a solution, that's the only solution from there, therefore linearly independent. It's your choice what machinery you want to use. That's just kind of up to you. And to be a bit explicit, if you plug this into a matrix, you'll have something that looks like this with a negative 1/2 and a negative 3/2 here. This and 0 and 0. This is pretty clear to say that, hey, the rank of this is 4. Okay, so now I'm up to here. So the next thing I need to show is that this thing is going to be a spanning set. So if I wanted to show spanning set by a definition, I would need to show that any arbitrary third degree polynomial, so any x in P3, or any p in P3, to be more consistent with the notation of R, I need to show that for any of this, this thing could be written as some linear combination of these things here. Okay, that'll be a bit tedious. I really don't want to end up solving that system by hand. So instead of proving that directly, I can use a fact that we've shown previously. P3 is a four-dimensional vector space. Yeah? Okay. L is a linear independent collection of four vectors. Okay. Well, that tells me that L spans P3. Why? Well, I know that any collection of n-linearly independent vectors in a n-dimensional vector space is a basis. So I can use that theorem here. Okay, so thus I conclude that L is a basis of P3. So you could, if you wanted, go through and solve that thing where I have P is equal to your A1 plus your BX plus your C times this third one plus your D times the last one. You could go through and do this, but that's going to be very tedious. That's going to take a lot of work. And the beauty of linear algebra is that we have all these nice theorems now that we can apply and simply just say, hey, this theorem works, let's use it, to save ourselves a lot of work. So keep in mind those type of tricks for the final. They can dramatically make things a lot easier and save you some time. Okay, so that is it for question 5. Now we need to look at question 6. What is question 6? Well, this is another one of these abstract vector space questions. Consider the collection of nth degree real polynomials with even coefficients defined by this term here. Okay, so just note here, x is going to be a real number, and these numbers a1, a2, up to an are just going to be even integers. Okay, so I have 2 questions. Is this a subspace of Pn of R? And further, is this a vector space over Z? So what do I mean by a vector space over Z? Well, here I'm just replacing the scalars in the definition of a vector space with real numbers. So to be explicit, by vector space over Z, I really mean to say take this definition exactly as I had it here, but instead of having this be the real numbers, have this be Z and call it a vector space over Z. Okay, so let's tackle this first question here first. Is this a subspace of Pn of R? So first, is it non-empty? Well, very clearly this is non-empty. Is it a subset of Pn of R? Well, yeah. It's just the elements of Pn of R that have even coefficients here. Okay, so it is a subset. It is non-empty. So the next question, is it closed under vector addition? Well, yeah, if I take something here and I add 2 of these polynomials of this form together, well, I just add the coefficients together, and the sum of even numbers is even. So this would be closed under vector addition. In this case, polynomial addition. Well, the last one, is this closed under scalar multiplication? That's where I run into a problem. If I take one of these polynomials and I multiply these things by some number, I'm not guaranteed that these will remain even integers. So to be explicit, I can just take this counterexample. Note 2 is an element of Pne of R, and 1/2 is an element of the real numbers. But 1/2 times this polynomial is just 1. 1 is not an even number, therefore it's not in this set. Okay, thus this thing is not going to be a subspace of this, since it's not closed under scalar multiplication. Okay, so the next question is, would this thing be a vector space over Z? Well, let's just look at those requirements to be a vector space over Z and just see if they're true or false. Okay, so the first one is the sum of 2 of these vectors a vector? Well, let's just think about this a bit. If I take 2 of these and I add them together, is that going to be one of these polynomials? Well, yeah, right? The sum of even numbers is even. I kind of argued that previously. So this one checks out here. And to kind of be explicit here, we do need to state to see if this is a vector space over Z, we check these defining properties, and I define these key terms here that I want to work with. Note C and D are in fact coming out of Z, as I mentioned here. They need to come out of Z. Here, they need to come out of Z. Okay, so now since V1 holds, I now need to check V2. Is this property true? Well, that holds for all polynomials, right? Pretty easily. Therefore, it holds for the polynomials of this form. Same thing for V3. This is true for all polynomials. Therefore, since this is a subset of the set of all polynomials, this would hold for this new proposed potential vector space. Okay, so all of these are true thus far. So now I need to show if the 0 vector is in this set. Well, is the 0 vector of this form here? Well, yeah, pretty trivially, right? 0 is an even number, so I could plug in 0 for a1 all the way up through an, and I can say, hey, since 0 is even, this 0 vector or 0 polynomial is going to be in this set here. So next up, I check v5. Here, I need to show that for every x in my p sub n comma e over r, that there exists this negative x such that they cancel out. Well, would that be true for polynomials of this form? Yeah, for any polynomial of this form, all of these coefficients would be even, right? So if I take negative of that polynomial, I just get negative these coefficients, and the negative number of an even integer is also an even integer. So here, to be explicit, since for every even integer c, the integer negative c is also even, it follows that for every p in this set of the polynomials with even coefficients, this vector, which is just -1 times it, is also going to be in this set, and it is going to be such that x plus negative x is equal to 0. That follows pretty immediately, right? Okay, and now we look at v6, which is the last non-trivial one of these. This is saying that if I take any one of my scalars and I multiply it by my polynomial, that's still contained in the vector space, right? Closure under scalar multiplication. Is that true here? Well, it wasn't true for real numbers, right? If I took my scalars to be real numbers, this was not true. But if my scalars are now going to be integers, I can say, hey, if I take an integer and I multiply it by an arbitrary polynomial in this set, I simply scale all the coefficients by an integer. And since the product of any integer c and any even integer is still an even integer, I can conclude that c times x would simply be one of these polynomials, given that x is a polynomial. Okay, that's nice. Okay, now for v7 through v10, all of these actually follow trivially since they hold for any polynomial that you want to pick. It has to hold for the even polynomials. So just kind of notice here, this one I had a little bit of work to do because I need to show that that this set was closed. For v2 and v3, these were trivially true because they were inherited from the set of polynomials, right? Similar, all of these terms were inherited from other polynomials as well. So that's thus the only one of these terms that I actually had to contend with were the ones where I was saying, hey, is this actually contained in this set that I'm proposing to be a vector space? So v1, v4, v5, v6. And generally speaking, if you're ever try to show that some object is in fact a vector space, and that objects that are in the set that you're trying to show that is a vector space come from another set that is a vector space, then these v2, v3, v7, v8, v9, and v10 will trivially hold due purely to the fact that you're dealing with a subset of things that are vectors within another vector space. Okay, so for instance, if you're working with the set of all polynomials and you want to show that a particular subset is a vector space, well, these things hold for all polynomials, therefore it'll hold for your set. Or say if we ask you to show that a subset of the set of all functions is a vector space, then these terms here will automatically become inherited just because it's a subset of another space, of another set that is in fact a vector space. So that said, you do need to mention that these things hold. It's just you can have a similar argument that was presented here. Just replace polynomials with whatever vector space it's coming out of. Okay, so just kind of a pro tip there. So here we want to conclude this proof, right? So we've shown that all of these things hold. Therefore, we can say, hey, this satisfies the properties of a vector space over Z. Therefore, it is a vector space over Z. Okay. Nothing super fancy here, just kind of chasing out all these details. And if I ever ask you to show something like this on, say, the final, this is what you would need to do. Show that all these properties hold. Okay, let's look at the next example. Example number 7. So here I'm going to give you a set of matrices, and I'm going to ask you, is this a linearly independent set? Well, what does it mean for something to be a linearly independent set? In general, that just means if you take an arbitrary linear combination like this, where C1 through C3 are simply real numbers, then each one of these things is equal to 0. Okay, so here, by the definition of equality in the set of all matrices, if this sum is equal to this matrix here, then the various entries will be equal to the same entry over here. So simply equating all of the entries together gives me a nice system of equations. So where's this coming from? Well, to be explicit, here I get my C1 plus 2C2 plus C3. That's just this term plus this term plus this term is equal to that term. The next bit gives me this term, this term, this term is 0. That's just coming from these terms here. Okay. And similarly, the third equation, all of this, comes from these third terms here. And this fourth one simply comes from these fourth terms here. Okay, this is simply a system of equations that we've solved before. How do we solve a system of equations? Well, I throw it into a matrix and I carry it to RREF. Okay, so from here, if I want to get these solutions, I simply take it in here and I row reduce it. Okay, so clearly at this point, there is only one solution to this, right? Here, this thing has rank 3 and it has 3 columns. Therefore, there's only the trivial solution. And I conclude that thus M is linearly independent from here. So that was pretty trivial. And in general, really, when dealing with these abstract vector spaces, the only thing you have to keep in mind is the definitions are a little bit different than what you had before with standard vector spaces, but not so much. And just apply the definition and kind of treat it like what you had before. So now let's look at question 8. So here I'm asked if this set spans P2 of R, and if it is a spanning set, is it also a basis? Well, here, if I want to show that this is a spanning set for P2 of R, I can simply notice something first. So instead of just going directly and saying, hey, pick an arbitrary element of this set and see if it's a linear combination, let's just notice that P2 of R is a 3-dimensional vector space. There's 3 elements here, right? So I could use the fact that if this is linearly independent, then it's a spanning set and also a basis. So that's how I'm going to go about doing this. And I'm going to consider this equation here to test for linear independence. So here the C1, C2, C3 are simply going to be real numbers. Well, similar to what I did before when working with the Legendre polynomials, I'm going to collect like powers. So here, if I look at x squared, I get C2x squared from this term here, and I get a C2 or C1x squared from here. Add them together, that's all of my x squareds. For x, I have a C1 from this term and a C3 from this term, and for my constant term, I just get minus C2 coming from that. Okay, so if this polynomial is going to equal 0, well, that tells me that the various coefficients here are all going to have to be 0. So from here, I can just kind of chase this out to find my solutions. Well, if I just look at this last term, this tells me C2 has to be 0. Okay, so if I plug this in, that gives me this is 0. So immediately that tells me, hey, C1 plus C2 is 0, but C2 is 0, therefore C1 is 0. That gives me that this term is 0, this term is 0, and now this term here has to be 0. Okay, so if I equate all of this to 0, I get C1 plus C3 is 0, or simply 3C is equal to 0. Thus, the only solution is C1 is equal to C2 is equal to C3 is equal to 0. Therefore, A is going to be linearly independent as a set of polynomials. So from here, notice that since, again, there's 3 elements of A, and P2 of R is a 3-dimensional vector space, I get that A is also going to be a basis for this set here. And from here, it is thus a spanning set. Okay, so definitely for these type questions, try to think smarter, not harder. You don't actually have to check to see if it actually spans it manually if you can show these other properties hold here. So just be cautious and think of those type shortcuts as you approach problems. It can, again, make things a lot easier on the final. Okay, now on to the last question for this tutorial. So does this set span the set of all 2x2 matrices of real numbers? Well, if this thing spans the set, then for any matrix that's a 2x2 matrix, it can be written as a linear combination of these. So I want to consider this set here, where each one of these C1 through C5 and these A1 through A4s is going to be simply a real number. Okay, so again, equating the various terms here gives me a system of equations. So here I'm going to have 4 equations with 5 unknowns. Okay, so my goal is to solve this. So it turns out you don't actually have to row reduce these all the way to notice that there is a solution. The only thing I care about is the existence of a solution. I don't care what the solution is. I'm not asked to show how can you rewrite any element of M22 of R as a linear combination of these things. I'm just asked, can you do it? Therefore, when I go to row reduce this, I'm not going to go all the way. I'm just going to partially do it. So here, this was my original system. So just plugging these in here gives me this augmented system. And here I can notice, hey, I have this one here. Let's use it to get rid of these terms down here. So if I do these 3 row operations, I can get rid of the ones down here. So if I do this, I simply get this term here. Okay, so now from here I can notice, hey, I have a 1 here. So if I put that up in a pivot position, that's nice. And I have a 1 here, so if I put this up in a pivot position, that makes things nice. So if I swap these rows to do that, I end up with this matrix here. So notice here, I have an element on all of these elements of the main diagonal. What does that tell me? Well, that tells me that the rank of this matrix will be equal to 4, and that's going to be the same thing as the rank of the augmented matrix. So by the system rank theorem, I know I have a solution. So I don't actually have to row reduce this any further. I can stop at this point. So in text, just to show how you could write this up, you could say, hey, we could row reduce this further, but it's clear that the rank of this matrix is 4 at this point. Since the codomain of the coefficient matrix is R4, by the system rank theorem, there is a solution to the system. This in turn means that there is going to be a solution to the original system of equations, right? If I can solve this, that tells me the coefficients C1 through C5 to solve this equation up here. Since there's a solution to the original system, I thus have that S has to span the set of all 2x2 matrices of real numbers. So yeah, definitely think smarter, not harder, because row reducing this is going to take quite a bit of work, right? So at this point, just changing these to 1s is pretty trivial, but then getting rid of the 2, the 3, and the 3, I have to do all kinds of, not horrid, but all kinds of linear combinations of these things. That's not going to be pleasant. So do take shortcuts where possible, but do make sure you explain why your shortcut works if you're doing something like this. So just give me a big text blurb here to say why it works. And definitely take advantage of all the theorems we've worked hard throughout this term to build up. They apply, generally speaking, to arbitrary vector spaces, so just make sure you do apply them where applicable, and where not applicable, don't apply them. So make sure you can justify why it does apply. Okay, so that is it for this final tutorial for the term. I wish all of you the best of luck on the final, and no matter what the results of the Evaluate survey is, Marmy does love you. She's just a little biased to the field of engineering that does have the largest percentage of students fill out the Evaluate form. Okay, so best of luck, and make sure you take a well-deserved break after all of your finals are done for the term.